Hello, Brother Alan. This is my final submission project for the week 6 learning thing. And if it doesn't look like I'm looking, that's me looking straight at the camera. I have my phone attached to it. However, I'm really excited to share this with you. So you asked for me to include my face. I'm sorry, that was really ugly. However, I'm ready to go for this. So for my project, what I'm building, I'm a physics major, and a project that I wanted to work on was a pendulum with driving force added to it. And so with that, I have all my files here. I have a pendulum class, and then I have a header file as well, where the header file, the header file is setting up our variables from there, making sure they're all good. Then our main pendulum class will be running everything. So I want to show you this particularly right here. If you see highlighted, that right there is called the Runge-Kutta-4 method. If you're a math major, you probably know what this is, or computer science. But it's a really useful method to try and essentially like process through the partial differential equation, and it will generate a really accurate probability or calculation of what it will be. It's like, if you think of Euler's method, this is a much more accurate method of doing it. And with that, I have it logged into reserving time as well. And then in our main, I have it set up so we will input the data ourselves, which I run a couple different tests down below, but I'll do one just for you. And I have it set up so it will save to both a TXT and a CSV file. So we're going to run it. I'll open this up just a bit more. All right, and a mass, we're going to say 1 kilogram. Length, we'll do 10 meters. Damping coefficient, we'll do 0.5. Initial angle, we'll do 2 radians. Gravity, of course, we know it's 9.8 meters per second squared. Time step, 0.01. That gives us a smallness thing, so as it keeps slicing, our max time is 72,000 seconds. And so the time step, the smaller it is, the more iterations through the Runge-Kutta it will do. But 0.01 is a pretty good time step for that. I'm going to hit enter, and our driving force, we're going to do 1.2 newtons. And then the driving frequency, we did 2/3 pi over radians, so which is 0.66. We'll add a couple more just for clarity's sake. We'll hit that to drive, and now that'll run. And as you can see, it was done in 2.74 seconds over these many recorded states right here. Now this is great because we have it saved to these TXT and CSV files right there. So I'm going to open up my Python work here now, and I've written up this code here to specifically read through that now. And I'm not going to include this, I'm just doing it just for clarity's sake to show you that it worked. So if I hit run right here, and as you can tell, that is what the Poincare, what specifically we are doing with the driving force of it, and it's just what it looks like, at least pi force out of phase and stuff. But we know it works, and that's the great thing. And yeah, that's my final project. I hope it works well. And so yeah, final project. I hope it works well, and I hope you have a wonderful rest of the semester.